So let's say we wanted to estimate this partial sum n less than x of the sum of divisors function at some complex number w of n chi. Here I'm going to assume that chi is non-trivial and the real part of w is strictly positive. So previously, we found that the Dirichlet series n from 1 to infinity of sigma sub w n chi over n to the s was equal to the product of the Riemann zeta function times this Dirichlet L function, L of s minus w chi. And the general machinery that we've sort of set up so far is that if you want to estimate partial sums like this, a really good way to do it is to look at the associated Dirichlet series and then use Perron's formula. So because we're assuming that the real part of w is strictly positive, this Dirichlet series converges absolutely for the real part of s is strictly greater than 1 plus the real part of w. So this is called the abscissa of convergence. So Perron's formula tells us that the integral 1 plus the real part of w plus epsilon minus it for some large positive real number, capital T, to, well, just along this vertical line segment of this Dirichlet series. So here we're going to have a zeta of s times L of s minus w chi, and then we multiply by x to the s ds over s. This is equal to the sum n less than x of this thing that we want to estimate, and then the error term from Perron's formula is big O of x to the 1 plus the real part of w plus epsilon, and then we have an over t here. Okay, so this is going to be the plan to evaluate what we want, right? So this is the what we want. What we can do is we can look at the complex plane, and we've got our abscissa of convergence. So this is going to be 1 plus the real part of w plus epsilon, and then I'll say that this corner, I'll just say where we are for the corner, that's right here. And let's shift, let's look at a rectangle going back to 1/2. So maybe this will be 1/2 plus epsilon plus it. And if we look at this contour, so C1, C2, C3, C4, and we integrate around it, well, Cauchy's residue theorem says that the integral along this entire contour of our integrand, zeta of s, L of s minus w chi x to the s ds, over s is equal to 2 pi I times the sum of residues of this thing, and this will be a sum in the rectangle. Okay. Now this integral along C1 of our integrand, so this is going to be zeta of s L of s minus w chi x to the s ds over s is more or less what we want. And when I say it's more or less what we want, what I mean is that by Perron's formula, we see this is an integral along C1, and it's more or less what we want because we have this one error term here. So let's put aside the integral along C1. We'll use Perron's formula later. And then for the integrals along C2, C3, and C4, we have to start bounding stuff. So if you use the convexity bound, then what you find is that zeta of s L of s minus w chi, when the real part of s is strictly positive, this is going to be less than, here we're going to have a absolute value of t to the 1/4 plus epsilon, where here I'm writing s is sigma plus it. And then for this Dirichlet L function, so we're going to have, so L of 1/2 minus, so this is going to be on the real part of s is 1/2 plus epsilon. So here, when w is, the real part is positive, this is going to be L of 1/2 minus w. So let me also assume that, well, yeah, we don't need to make any further assumptions. So we have the value at s equals 1, and we have the value at 0 for this Dirichlet L function. And over here, you grow like t to the epsilon. So I'm going to say your epsilon over here. And at 0, using the functional equation, you can find that you grow like t to the 1/2 plus epsilon. So the convexity bound says that you have this linear interpolation between the two. This extends further in the other direction. So this line is t to the 1/2 minus sigma over 2 plus epsilon, right? That's how you're going to get a value of 1/2 here and a value of just epsilon here. Where sigma here is the real part of s. So this product is going to be t to the, now we have a 1/4 minus the, or plus the real part of w over 2 plus epsilon as the bound, the convexity bound for this Dirichlet L function. Okay, and this is going to be equal to t to the 1 plus the real part of w over 2 plus epsilon. So what that means is that our integral along C4, which was the left edge of our rectangle, of zeta of s L of s minus w chi x to the s d s over s, using just this bound and some straightforward bounds, we get that this is going to be x to the 1/2 plus epsilon, and the power of t that we're going to get is t to the, well, this much, because we have a 1 over t here, essentially, but we're integrating from minus t to t, so we get 1 plus the real part of w over 2 plus epsilon. For the bounds on C2 and C3, which were the horizontal segments here, the bound is smaller, right? You can essentially just plug in the endpoints of your integrand, because you're using the triangle inequality. You're just integrating exponential in x. So what you end up getting is that this is x to the 1 plus the real part of w plus epsilon, which was the abscissa of convergence, and then you have a divided by t here, so it's using this convexity bound. It's this much minus t, or t to the this much minus 1, so minus 1/2 plus the real part of w over 2 plus epsilon, and we'll see that this ends up at the left edge of the, this is at the right edge of this segment. You're just going to get a t to the minus 1, because these series converge absolutely. You use the triangle inequality, so you just have a 1 over t from this, and then it's the left edge, x to the 1/2 plus epsilon t to the minus 1/2 plus the real part of w over 2 plus epsilon at these corners here, this one and this one. And you can see that this is going to be less than the contribution along C4, and this is the contribution we got from Perron's formula. So as usual, you don't really have to worry about these. So what we end up getting is that the sum n less than x of the thing that we're interested in, sigma sub w n chi, is equal to 2 pi I times the sum of residues, which we haven't talked about yet. And then what is the error term we're going to get? We're going to get this x to the 1 plus the real part of w plus epsilon t to the minus 1 from Perron's formula and from this term in the horizontal segments. And then we're going to get this contribution from C4 of x to the 1/2 plus epsilon t to the, then we had a 1 plus the real part of w over 2 plus epsilon. And we want to make these two error terms equal, so let's do that. Let's say that t is x to the alpha, then dropping the epsilons, this first one is going to be x to the 1 plus the real part of w minus alpha, and the second term is going to be, so maybe I'll put in the epsilon here, and here we have an x to the 1/2 plus 1 plus the real part of w over 2 times alpha plus epsilon. If we want to balance error terms, let's set 1 plus real part of w minus alpha to be equal to this exponent. And okay, let's solve for alpha and see what we get. So we're going to have this 1/2 plus the real part of w on the left-hand side, and on the right-hand side we're going to have a 1 plus the real part of w over 2 times alpha. So we should take alpha to be equal to 1/2 plus the real part of w over 1 plus the real part of w over 2. And this we can clean up a little bit. This is going to be 1 plus 2 times the real part of w over 3 plus the real part of w, right? Okay. And what that means is that the error term we end up getting is x to the 1 plus the real part of w, and then we have t to the minus 1, and t is x to this much, so minus 1 plus 2 times the real part of w over 3 plus the real part of w, and we have a plus epsilon here. So that's the error term we end up getting. Now, for the sum of residues, well, let's look at our integrand, zeta of s L of s minus w x to the s ds over s. This is our integral. And, well, maybe I'll just talk about the integrand. So in this region, the only pole is at s equals 1, right, where you have the zeta function has a pole there. So what you end up getting is that the sum n less than x of sigma sub w and chi is equal to 2 pi I, and now the residue of this pole is 1, so we have this coefficient of L of 1 minus w chi times x, and then our error term is O of x to the 1 plus the real part of w minus 1 plus 2 times real part of w over 3 plus real part of w.